All right. Now we're going to talk about how to move around charges. We've talked about charges. We've talked about them in the context of protons and electrons, as in electrons carry a negative charge, protons carry a positive charge. And what I can do now is I can exploit the word carrier and move them around. Of course, they have to be able to move to do that. We're going to see some situations in a second where some charges cannot move around. But if I have a charge carrier that's able to move, I call it a mobile charge carrier. And what I can do then is I can put that charge on different objects and thereby do what we call charge them. I give them a net positive or negative charge. The simplest way to see that is by considering an atom, which is made up of a nucleus with positive protons, an electron cloud with negative charges. If I take a negative charge away, that is, if I remove an electron from an atom, I have left the atom with a net positive charge, right? It has more. I'm assuming I started with a neutral atom. But if I take an electron away, I now have more protons than I do electrons. Therefore, I've left it with a net positive charge. Of course, if I put an electron on the atom, which I can also do, I have now left it with a net negative charge. It has more electrons than protons. In chemistry, you probably learned, or you will learn if you haven't taken chemistry yet, that process is called ionization. Removing or adding electrons to an atom makes an ion. An ion is a charged atom, basically. So if I take an atom and remove electrons, I now have the possibility of two different kinds of charges move around. I've got an electron that I've taken off that can move around. I've got a positively charged ion, which if it's able to move around, can move around, such as in a gas, a hot gas, or if I really heat the gas up and make it into what we call it a plasma. I've got the possibility of negative charges moving around. I've got the possibility of positive charges moving around. If I'm dealing not with a gas, though, with a liquid or solid, or we'll leave liquids off for now, but if I'm dealing with a solid, well, what I have usually is the atom is locked into some sort of rigid structure, so it usually can't move, but the electrons are then free to move. And even with that, though, in some substances, the electrons aren't very mobile. So I can put electrons on and take electrons off, but once they're on or off, it's difficult for them to move around. Not impossible, but difficult. Some substances have electrons that are really easily moved around, right? So the difference that we're talking about is in the difference between conductors and insulators. When I say the word conductor, what I mean is a substance that has highly mobile charge carriers. Usually, in real life, that is when I say real life, most of the examples we deal with of electricity in the real life deal with solids, electricity flowing through a wire, things like that. So if I'm dealing with those, the charge carriers almost always are electrons. If I have a gas, like in a neon discharge tube, I've got the possibility of positive and negative charge carriers. This can lead to some really obnoxiousness, because that means if I'm really going to characterize the system mathematically, I've got to know, is it the negative charges moving around? Is it the positive charges moving around? Is it both of them moving around? Fortunately, though, the mathematics comes to our rescue. Remember from your study of mechanics that negative and positive signs are always associated with direction of motion. Well, now in electricity, I've introduced other positive and negative signs, but that doesn't mean that the directional element has gone away. It just means I have something else to add to it. As it turns out, because of how the math works, which we'll see as we go through the rest of this course, a negative charge moving one way acts on paper and in real life just like a positive charge moving in the opposite direction. That's a nice simplification, because what that means is if I'm going to characterize electrical systems or charges, in this case, charges and charges moving around, I don't actually have to know if it's the positive or the negative charges moving. I can just pick one and characterize the system using that, and I get the same answers that I would get if I had picked the other one and done the directions right. So of course, because we don't like dragging negative signs around more than we need to, we're going to assume that any motion of charges involves positive charges moving. In real life, it very well might be that what's actually happening are negative charges moving the other way. We don't care in some sense. Of course we care, because we want to know what's actually happening. But if we're going to characterize a system, and I'm going to get the same answer either way, I'm going to pick whichever one is easiest, and that's usually to deal with positive charges. So I'm going to do some charging demos here and talk about, I'm putting charges on this. I might very well be taking negative charges off as opposed to putting positive charges on, but it's going to work the same way. Okay, so we have conductors, which are materials with highly mobile charge carriers. You might recognize those as usually what we call metals. Metals, we all know that metals conduct electricity, right? But why? What makes their charge carrier so mobile? Well, as it turns out, the electrons in metals, or in all substances, are arranged in certain levels, energy levels or shells. In metals, the outer shell, which is called the valence shell, has a low occupation number. There are not many electrons out there. What that means is that they're really easy to take away. So it's easy to strip electrons off metals and send them down a wire or what have you. An insulating material, which does not have highly mobile charge carriers, usually have high occupation outer shells or valence shells. Things like lucite, right? This is a piece of basically plexiglass. This is an insulator. It does not have a large set of highly mobile charge carriers. This plate on top of this, what's called an electroscope, is made of brass. Brass is metal. It's got lots of highly mobile charge carriers. Now, what I didn't say is I couldn't put charges or take charges off of this thing. What I am saying is once I do that, there's some means they have difficulty moving around. This is an insulator. For this metal, they can move around however they want to. They're highly mobile. Okay, so what are we going to do with this? Well, I'm going to illustrate a couple of charging processes by which we are able to move around charges. The first one I can say is we can charge rods like this by friction. I have here a piece of felt. If I were to rub the felt on this rod, that would impart charges to the rod, right? Now, some of you might have done this already. Some of you, I certainly would never do something this evil, but some of you may have. I don't know. I'm not here to judge. At some point when you were a child, if you had siblings, and in the winter, you might have taken off your shoes and rubbed your feet around on the carpet in your socked feet, right? And then snuck up on your sibling and touched their bare arm when they weren't looking. What happens? Well, if you've done it right, they get a nice little shock. You do too, but you're expecting it. They're not expecting it, right? I, again, certainly would never have done that to my super sweet big sister who always went out of her way to make my life better. But some of you might have done that. What you're doing is you're charging yourself by friction. You're actually physically rubbing charges onto yourself or taking charges off of yourself. It doesn't really matter. I could do the same thing with this rod. I could rub it with this piece of felt and give it a small charge. Now, the felt works okay. I have a piece of silk here that also works. But you know what works the best is cat fur or rabbit fur. But for generations, physics students have walked into physics lectures and witnessed the horror of their professors pulling out a cat pelt and rubbing it on some sort of rod to charge it up and showing them the charging process. I'm not going to do that to you, but I just so happen to have a better version. So I have here the live version of that demo, right? This is Luna. She's not really super excited that I disturbed her nap. But let me do this. What I'm doing, she thinks I'm petting her. I'm actually giving this rod a little bit of charge, right? I'm actually putting charges onto this rod. Of course, those charges have to come from somewhere charge is conserved. So they're coming from Luna. Now, let me show you what happens if it works. Conditions have to be right. There we go. Thank you. Back to your chair. So what I did is I put charges on this rod. That is called charging by conduction. Now, charging by conduction can cover a couple different things, but the point of charging by conduction is there is a physical path for the charges to flow onto this rod. So in this case, that was just by friction. What I did then, though, is I took this rod and I touched this metal plate, and you should have seen this lever in here move. And in point of fact, it's still moved. So let me explain how this works. How this is set up is this top metal plate goes through the shell and is connected with the metal armature down here. So this is all one piece of conducting material. What makes a conductor a conductor? Mobile charge carriers, right? So what happens is I put a bunch of positive charges on this rod by rubbing it on the poor cat. And then I brought it close to this plate, and you should have seen something happen. When I touched the plate, you should have seen the lever move. Why did it do that? Well, positive charges, we know, don't like to be near each other. So I had a bunch of positive charges on this thing. In point of fact, I probably had negative charges, but we're going to assume that they're positive charges. They don't like each other, but they have no choice to be near each other because I forced them to be here. But when I touch this metal, some of them have the opportunity to jump ship, as it were. And they do so. They jump into this metal. Of course, what happens then is that the metal, which has lots of charges that are able to move around, those positive charges don't like these positive charges, and so they all spread out as far as possible. Imagine being put into a room with 10 other people and none of you like each other. And not even that, you can't even tolerate each other. What are you going to do? You're going to move to positions where you are as far away from everyone else as completely possible. That's what these charges in this plate do. I gave this plate an excess of positive charge. That positive charge was immediately distributed throughout the rest of this metal, and they all went as far away as they could from each other. But part of this thing can move. That lever can move, and so the repulsion of those positive charges made the lever move to a position in which it was as far away from its neighbors as was possible. In point of fact, those charges, after a really small increment of time, come into equilibrium. Of course, the positive charges are exerting forces on each other. They're moving in accordance with those forces, but they come really, really quickly to an equilibrium position in which the forces summing up on the charges is exactly zero. Doesn't mean there are no forces. It means the net charge is zero. So I charged the rod by conduction. I charged this by conduction, right? There's a physical pathway for charges to get off the rod onto this. I touched it, right? Let me do it again. You notice that this went back to a normal position, right? Why is that? Well, the charges are going to leak off into the air, and that depends on how humid it is, how dry it is. Humidity usually is able to take charges off because the charges attach themselves to water molecules floating through the air, and here in the summer in Alabama, it's nothing if not humid. So let me do this. I'll let Luna finish her nap. Oh, come on. Like I say, conditions are not great for this today. Oh, come on. I'm going to have to get the cat again. I think I am. Sorry, Luna. It's for science. I know. I'm going to be her least favorite person for the rest of the day. Again, these demos work really well in the winter when it's dry. Not so much in the summer. I know. Just hang on. Still not working. 2 seconds. There we go. All right. Thank you, Luna. Now, let me try to give this rod a little bit more charge with this. Let that come to a position. Now let me show you a different sort of charging. So if I can charge up the rod again, what I'm going to do is I'm going to bring it close, but not touch the plate. Come on. Huh. This would be fantastic in winter. And Luna has left the room, so there's no opportunity for that. That's okay. Let me talk about what should have happened. So if I don't touch this thing, if I just give this rod some charge and bring it close to this plate, what should happen? Well, the positive charges in this rod are exerting forces on the positive charges in this plate. So what happens is that they retreat, right? They're able to move, no big deal, so they migrate down from the plate. That, of course, leaves the plate with a net negative charge, and this falls down, or the positive charges are pushed down, and you would see the lever move. And so I have a net negative charge on the plate, a net positive charge down here. But if I never touch the plate, if I never give the charges a physical path to move around, then there's no net charge of the whole object. There's a charge here, there's a charge here, but the total charge hasn't changed because I haven't given the electrons or protons any opportunity to move around. I'm just moving, or I should say, any opportunity to move off of this object. I'm just moving them around within the object. So I'm creating regions of charge. In that case, it would be regions of negative charge here, regions of positive charge here. What I've done, in fact, is I have polarized the object. I have moved charges to different regions without changing the net charge. We call that, we call it polarization, but we call it charging by induction. Induction creates regions of charge separation without putting on a net charge. Sorry, one more time to get this thing working. It's just going to be stubborn today. I'm not going to disturb my cat again. But that's the idea. Now, what I said a while ago is after this thing was charged, charge started leaking off into the atmosphere, right? Which it does, slowly. I could have discharged it quickly just by touching it. Think of what that would do. That would give all these charges the opportunity to get away from themselves, which they don't, or get away from their neighbors, which they don't like. To do so, they would have had to come on to me, right? It's exactly what you're doing when you shuffle your feet across on the carpeted floor. You are putting charges on yourself. In effect, you're connecting this object to what can be considered to be a C, an infinite supply of charges, positive or negative. We have an infinite supply of positive charges and negative charges in the Earth. We consider the Earth to be this infinite sea of charges which we can add to, we can take away from without affecting anything. And so the best way to ensure that the charge flows off of this object is to do what's called grounding it. That is to say, connect some sort of conducting material from this object to the ground. That's really what that means. I love the British version of that. They say they earth it. They say this object has been earthed. Here in the States, we say grounded, but it means the same thing. We're actually taking a physical pathway from this charged object to the ground to enable the charges to flow off of this object. So that is actually a pretty usual way to charge an object, is to connect it to a ground, bring an already charged object close to it, redistribute the charges, which in this case would mean that the positive charges are retreating from this plate, flowing into the ground, and then break the ground connection, remove this object, and the charges that left this metal don't then have the opportunity to get back on it. So I leave it with a net positive or negative charge, depending on the charge of this object. All right, that's enough for this time. So that finishes this section, I should say. Hope to see you in the next section.